Is the presentation visible?
Yes, we can see this.
Okay. Okay, so let us start. We'll do a couple of minutes of quick recap and people will complete joining by then. So I started talking about the binding protocol, and actually in the last discussion I talked about 4 properties of a symbol, and I just talked freehand and I did not have a slide on that, and I felt there was some expectation to have slide. So now I have added 4 slides on each of these properties. First is naturally the declaration. Every symbol will have a declaration which states its lexical name along with the data type and identifier. Next is a symbol which is a variable symbol. Along with the declaration may have an initialization, which is usually a compile time constant expression. And third is it will have a definition. Definition for a variable is every time it is assigned a value is written into that variable either directly or indirectly. It is a definition. For a function, it is the function body, which is called the definition. And finally, we have the binding, which is the physical memory address of the symbol. Okay. And this physical memory address certainly will not be known at the time of compilation. So at the time of compilation in the symbol table, we'll have the declaration information, name, type, size, all of that, initialization constant. In the code that we generate in the 3 address, we'll have information about possible definitions that are happening at multiple places. But the binding will not be present directly there. We would rather have to create a scheme by which the binding will get created at the runtime in terms of the activation record. So this is what we had discussed. So we saw that this is compile time. You have symbol table with this information in the target code. Finally, you have to have code for the activation record, which has the similar information about the symbols. In addition, it must have stack management information, return address, return value, saved registers and all that, and as well as the call return protocol, which we are going to talk about today. We saw a basic translation from in the front end from the 3 address, from the C program to a 3 address code and the corresponding symbol tables as well. How will typically the symbol table entries would look. The notable here is the fact that we are recording a kind of offset, positive and negative offset with each and every symbol, which needs to have a memory. Okay. So these are for help for final translation to the activation record. Then we talked about having memory different segments in the memory, text for program code, const for program constants, particularly string literals, static for global and non-local static values, heap and stack for dynamic and automatic variables. Okay, so now I come to what will be there in the activation record. Naturally, in the activation record, I will need to have the actual parameters because activation record is corresponding to a function which is being called, right? So it is actual parameters used by the calling procedure or the caller who will have to put these values of the actual parameters. Right. We will see often these could be done through registers also, but initially let's not get into that complication. Then we need to have a place for return value, so that when the called function would finish its computation and it executes a return, then it returns the value, and that value has to be placed somewhere in this record so that the caller can get this value once the control has gone back to the caller. Then we have return address to remember the value of the program counter to which the called procedure must return. Then we'll have a control link, which is typically a pointer to the activation record of the caller. Right? We will often need this. So the callee's activation record will be on top of the caller's activation record, and this is a control link to refer to the caller's activation record if we need. Then we may have an access link to locate data needed by the called procedure which are not a part of the activation record. So this is primarily for the non-local data. Then we have machine status. This is basically required because the CPU has a fixed number of registers. So when a function is called, the caller function is already using those registers, and those registers have live values stored in them. So once another function is called, the called function will also use the same registers. So the values in those registers that the caller had will get lost. But once the called function returns to the caller will again need those register values. So when the call happens, we need to have a space where the registers whose values need to be remembered can be saved and restored back. Then we'll have local data belonging to the procedure, which are basically the local variables that the function has, and the temporary variables, which are the unnamed temporaries that the compiler has generated. So this is, I mean, leave or take a few items, because this is not a standardized structure, but rather a scheme. So in some compiler, the activation record may have more information. In some, it may have a simplified one, and so on. But this is more or less what you logically need to be able to call a function. Okay. Now let's quickly look at the dynamic side of the call, which you all know. So I will go pretty fast, but just as a reminder. So purposefully, I have taken a recursive function. So Fibonacci, you all understand this. So when we translate this Fibonacci, so n is less than 2. So you put 2 to temporary. Do a if n less than t1, which is n less than 2, go to 100. So if it is less than 2, what do? You return n. So you go to 100, come here, return n, which is basically you have n already computed. So you return that value and go to 102, which is the end of the function. Right. So here I have put a self loop just to indicate that you are at the end of the function. Now, otherwise, if n is not less than 2, then you go to 101. That is, you will have to come here in the else part. 101, you compute n minus 1, put it as the parameter, call Fibo with one parameter. Get the result, return value in T4. Again, call compute n minus 2, put in the parameter, call Fibo with one parameter, get the result in T7. So now T4 and T7 are added to get the final value, which is T out, which you return, and after returning, you come here. And in the main, I have not shown these are initializations. So I have not shown those initializations. So you have a call to M, param M, call Fibo with one parameter, get the return value, put it to F. So this is so what you have on right is actually what its assembly version is what will actually execute along with the activation record. Right? So if I call Fibo 4, this will be the call graph. Very easy to see. So what will happen if what I'm trying to look at is the activation records on the stack. So here, each one of this I've written activation record for which function. PRM stands for the parameters. RV is the return value, which I do not show. And link is the link to the parent's activation record. So first with the main. So when main is called, that its activation record is created, AR of main. And main is called from whom? So I'm assuming that there is a function called CRT main, which is calling main, right? Which is in some compiler on Windows, this is the reality. It could be something different in other compiler. Now main calls Fibo with 4. So parameter is 4. So the activation record of Fibo 4 comes on top of this. Link to activation record of main stays. Then Fibo 3, because you are first calling on n-1. Then you have activation record of Fibo 2, again on n-1. Fibo 1, again on n-1. And Fibo 1 actually gets the value. So it returns to Fibo 2. So this part of the stack does not change. This is the top 4 parts. And then you have a call to Fibo n-1, n-2. So you call Fibo 0, which is also evaluated. So once, so this is done, Fibo 2 is done. So now from Fibo 3 up to Fibo 3, nothing changes. And you have a call to n-2 again. So Fibo 1. So it continues like that. Left reference depth first search on the call graph. So this is what is happening. So what we will have to decide are two things. One is how this layout will be, and what will happen when a call is happening, when the activation record is supposed to come on the stack, and what is happening when the return happens, when the activation record is supposed to disappear from the stack, with all values remaining consistent. So we have what is called a calling sequence and a return sequence. Calling sequence consists of code that allocates the activation record on the stack. See, at any point, the caller's activation record is on the top. Now the caller is going to call a function. So the calling part, call can be possible only if the called function gets its activation record. So that activation record will have to be allocated on the stack. And be careful about this word allocation. This allocation is not like a dynamic allocation like malloc and all that, because it's known to be a given area stack is consecutive, growing in one direction. So the allocation here necessarily means that reserving certain part of the next consecutive bytes beyond the current activation record for the activation record of the called function. Now the calling sequence is divided. So some code will have to execute for that. So calling sequence is divided between the caller and the callee. Some part the caller will do, some part the callee will do. We will see why. Other part is the return sequence, which restores the state of the machine, which is the values of the registers that caller had been using, and can continue its execution after the call. That is a return sequence. Again, to be done jointly by the caller and the callee. So look at this diagram carefully. Leftmost is a schematic of the stack. So this solid line to solid line is one activation record. So what all do you have? You have temporaries and local data. Just remember all that we said in terms of the activation record content. So you have temporaries and local data. You have links and saved status that is linked to external data and so on. And the saved status is the registers and all. You have a control link to the parent's activation record. You have parameters and return value. So this is all that you have. And then the next is the function you have called. Again, the same type of values for the function. Okay. And somewhere around this point between the links and save status and temporaries and local variable, you have the top of the stack pointer, which is the content of the stack pointer register, right? We will see why it is in the middle. Now, you see the responsibilities. This is this part. So leftmost was a layout of the stack. Then the next is basically a logical partitioning. So leftmost and the rightmost columns mean the same thing. So callee's record, on top of that caller's record. Stack is going upwards, growing upwards. Now in the middle, we are showing what the responsibilities are. The caller's, this is caller's responsibility. That is, the caller will have to take care of this part of, that is some part of its own stuff and some part of the caller's record. I'm sorry. The stack is not going upwards. The stack is going downwards. I'm sorry. Very sorry. Just get me corrected. The stack is going downwards because top here is the caller's record and then is the callee's record. So this is what exists and below this is what will come now. Okay. So stack is going downwards. Now, so what will the caller have to do? See, caller have to pass the parameter, right? So, and that parameter has to be in callee's stack frame, right? So the caller has to write this parameter in the callee's record. That is why it is in caller's responsibility. After the callee has finished, the called function has finished, it will leave the return value as a part of its activation record. And caller has to pick it up from there. So you can see that the parameters and return value are very conveniently placed at the boundary of the two activation records so that the handshaking can become very easy. So even before the callee has started executing, that is, this activation record has not happened, caller can go ahead and write the parameter. Then it gets called, the callee does the computation, all that. The callee returns. So logically, the activation record of the callee disappears. Logically, physically it will be there. Okay? And then caller gets the control and take out the return value from the callee's part of the activation. That's a key part that you will need to really understand. Okay? So naturally, it's the caller's own temporary local data are certainly caller's responsibility. Callee's temporary local data certainly is callee's responsibility. Also see that the saved status is the caller can decide that this is all what I want to save before I call, or it could be in callee also doing that. So this is a typical calling sequence. The caller evaluates the actual parameters. That's the first thing required. Right? The caller stores the return address and the old value of the top of stack into the callee's activation record. Okay. Because caller only knows that. Once call has been made to the callee, return address will not be known. So it has to write the parameters. It has to write the, it has to write the return address. And it will also have to remember the current value of the top of the stack. Caller then increments top of the stack to the positions shown. So back on the slide 16, caller will then increment. So the top of the stack as if goes here, as if then the callee's activation record has come into place. The callee saves the register values and other status information. The question is, why does callee save the register values? Caller could also save that. Callee can save register values based on the registers that it is going to use. It may not touch the other registers. Caller can also do that. You'll have to settle on one protocol. So here what we are discussing is callee saved status. Then callee has to initialize its local data and begin execution. It's a call sequence. Parameter, return address, top of the stack, machine status, and initialization to start execution. Next, slide 6.19. Now the return sequence has to match the calling sequence. So callee will place the return value next to the parameters, as we have. Using the information in the machine status field, callee will restore the top of the stack and other registers. So it had saved them, it is restoring them. So once it restores, then logically the stack, the activation record, the stack frame is logically removed. And then it branches to the return address. So it basically makes an indirect jump to the return address that the caller had placed in the status field and goes back to the control, goes back to the caller. The caller's, the top of stack has been decremented. So we are currently in the caller's activation record, but still the caller knows where the return value is by the side of the parameters. So it can always go to that location with respect to the top of the stack and get the value and proceed. So this is again. Is there any question? Or it is clear, or post lunch, people are a little bit.
No, sir, it's clear.
I hope the slide is visible again. I'm on 6.20.
Yes, sir.
Okay. Yes, sir.
So now what I'll do is the simplest of case, but which will very easily generalize to a lot of other cases, is we will take up the case of a function call with int data type. So the same that we saw in the translation, the add function, the main function, which passes two parameters to add, and the three address code corresponding to it, the symbol table, just the earlier slide reproduced. Nothing special in that. Just to recap, main has three locals, A, B, C, It has two parameters, argc, argv, and it has two temporaries, T1, T2. Of the locals, A and B is passed to add as parameter, which add function has two parameters, x and y, and one local variable z and one temporary T1. So this is the logical translation into the machine independent code. Now, coming to the 6.22, all that I have done is I have done some what is called peephole optimization. That is, if I go back again to 21, T1 is x plus y and z assigned T1. So I can always remove this T1. I have z assigned x plus y. So that way I have done some peepholes. So A assigned 2, B assigned 3, like that. So as I do that, naturally, actually all temporary variables disappear. So that's a people optimize simpler code. Okay. Now I get into what you have been doing in the assignment 1. That is, look at the assembly language code. Right? The translation for this. Remember again, going back to 6.22, remember that I'm showing you for this code, which is already peephole optimized. So there is no temporary here. Now this is the main function, translation of the main function in the x86 assembly. So public main, and we are in the text segment, right? Because we are looking at code up to the end. It goes over 2 columns. It's up to the end where text segment ends. Then this is a procedure, main procedure, which ends here. And this is the allocation of the variables in a logical manner. These are allocations of the variable in a logical manner. It says that what is the size of the variable and what is its offset. So you can see that it puts the parameters on one side and it puts the local variables on the other side. So these are positive offset, these are negative offsets. But the whole idea is you have a consecutive allocation. So minus 12, before that you have minus 8, 4 bytes. Minus 8, you have minus 4, 4 bytes. Minus 4, you would have expected 0 here. But you have 8. So there is a difference of 8 bytes. Something is happening there. We have to see. Right? We'll see what is happening there. And then argc is 8. And 8 plus 4, 12. argv is 12. Right? So A, B, C, argc are 8. So they are 4 bytes. And argv is pointer. It is also 4 byte. We are talking about a 32-bit system. So this is the translation. So I've taken the assembly output embedded with the source. So this is the translation of this line. And then comes the declarations and definition of A. So we first start with EBP. EBP is an extended base pointer, which is taken to be the pointer of the activation record. Right? So I do push EBP. So I'm pushing the base pointer on the stack and then move ESP to EBP. That is the current stack pointer. After this push, we make it the base pointer. Right? Then subtract 12 from the ESP. This is in hex. This is 12 in the ESP. Why? Because that much of local variables you need. You need 12 bytes of local variables. So I'm creating the space for the local variable by subtracting from that stack top. Then I do an initialization. So what is EBP? EBP was where I have put the stack pointer. That is a base pointer of the activation record. Then I have subtracted 12 from the stack pointer to make sure that I reserve 12 bytes, because beyond this point, if I do any push pop, anything that will happen after leaving these 12 bytes. Okay? So now I go back to EBP and I fill up, initialize these values. As such, you can see there is no initialization given. So what I do is I initialize with a very specific pattern, which is again compiler dependent. It's all C's, and that is this is done in the VC++ compiler, and there is a specific reason of why it is all C's. But that reason is, by the side. We'll come to that later. So this is basically the after allocation of the space, automatically EBP minus 12 is C. You write anything to EBP minus 12, which is what you are doing by this move. You are taking this value, moving it to EBP minus 12. So EBP minus 12, EBP is a word pointer, that is 4-byte pointer, D word PTR, and move the value there. So you are basically, where that is in memory, you are putting this value. So A, B, C are initialized, done. Then you have A assigned to. Next. So what is A assigned to? A assigned to is A is at -4. So it is EBP minus 4. So that is what you are writing here. But you are writing this this assembler uses a little, in inverted notation, you can say it is EBP is the beginning of the array, and underscore $A is the offset. Rather, it writes the offset as an array name and EBP as the offset. Right? But it comes to the same thing. It is EBP minus 4, which is the address of A. Take a pointer, assign 2. Similarly, B, assign 3. Add AB. So what it does is, so stack pointer now is here. Remember, I've jumped 12 locations. So stack pointer has covered all this. Now I have to do this add. So I have to compute the actual parameters. Here there is no computation involved. So the parameter is known. It is B. And this has idiosyncrasy to scan from right. So, so B, I take the value of B, put to the register EAX, push EAX. So what I have done? On top of these local variables, I've put my parameter B in the consecutivity. Then I have again taken parameter A, moved it to ECX and pushed. So on the top two that I have pushed are now my two parameters that add needs. So add will have to know that. So we'll go to add and see how add knows that. And then we call add, which basically means that on top of this call, it is not jump. It is not jump, it is call. So call has the side effect that the return address will automatically be pushed to the stack. So here above the parameters, the return address will go in. And then the jump to that add underscore add location will happen. So add gets called. We'll go and see what is happening on the add. So we have B, A, then return address has gone in, called add. Suppose add has finished everything and it comes back. When it comes back here, naturally it has come back through a return. So the return address, which was topmost in the stack, has been consumed through the return. So when it comes back, on the top of the stack are these two parameters, which has no use anymore. So this was the calling sequence part for the caller. And this add is the return sequence part for the caller, where it has to do is to remove them from the stack obviously there's no point doing pop or anything. What you simply need to do is to increment the stack pointer by 8 because they are 4, 4. So just increment the stack pointer by 8, add 8. So that is effective of popping out params. It has used a protocol where the return value has not been sent to that activation record, but it has been sent through a particular register EAX. So EAX has the return value. So that is the value of add AB. So it has to be, C will be defined with that value. So you assign EAX to the variable C. You are done. You are ready to make return. Right? So what you'll have to ensure? You'll have to ensure that when you return, the stack top and the EBP must get the values you started with. So what all did you do? You have pushed parameters here. You have done a implicit push of the return address here, which has got nulled. Pushed parameters have been removed. So what is remaining in the stack is these 3 variables. That is, you had subtracted 12 from the ESP. So now you have to take them back out. So you add 12 with that. This 12, you are adding it back. So the local variable space that you had created is gone. So now what your stack is, ESP is, it must match the EBP because that is where you started. You had moved ESP to EBP. All the increment decrement that has happened up to this point, that should get matched. So at this point, again, EBP and ESP has to match, and that is not a necessary logic for translation, but that's called a runtime check. If this match does not happen, then there's something wrong that has happened in between this call and return. Okay? So if this is not, that has not matched, that is, if this comparison is not 0, then you have a problem. Once this is done, then you move EBP to ESP. This move is unnecessary if they're equal, but it's required if you have if they're issuing the check. And once that has been done, your stack pointer is at the right place. Top of the stack is EBP that you had pushed, and that EBP is popped back. So you get back the base pointer of your parent's activation record. Right? So this is the only thing that you have to do. Here there is a XOR of EAX, which basically sets EAX to null, which is required for the run routine. Okay, so this is what the main, caller side of the protocol. Let's look at the callee side. So the add function, again, does not have a temporary. It has one local variable and 2 parameters. So local variable, like before, is on the minus, parameters on the activation record pointer of the parent, who is main. Move the stack pointer to EBP, which becomes current. Push ECX. What is ECX? ECX was here. A. Push, but that is not what is important. What you are doing is basically, by doing this push, you are creating a 4-byte space. This push is a garbage. Whatever you push, that value is garbage. You do not need that. All that you need is like earlier you did subtract ESP12. Similarly, here what you want to do is subtract ESP4, because there is one local variable of size 4 only. So that, compared to that subtract, a single push is more efficient in terms of number of cycles. It's a single cycle operation. So this push is done. whatever value gets pushed does not matter, because immediately after that, in the EBP -4, you are putting the initialization, and that is initialization for Z. Then you have Z assigned X plus Y. So you take X, move it to EAX. You take Y, add it to EAX. So EAX now have X plus Y. You take EAX, move it to Z. So Z has got the final value. So you return. So you move. You are, as I said here, it is returning through the register. So you take this value of Z and move it to EAX. You can see that if you do a further round of optimization, then both of these moves will actually null itself and go away, because neither you have a later on use for Z, and you are moving EAX to Z and Z to EAX. So basically it's the same. I mean, not doing anything. So then you have to return. So what you'll have to return, you have to restore the stack pointers. That is, move EBP to stack pointer and pop the EBP. So this is the prolog part of the calling, and this is the epilog part of the calling. Goes back, as it goes back on slide 23. This is the point where we have landed with the parameters on top. Okay. So let me stop here again and check back on how you are doing.
Hello, sir. I have a doubt.
Yes, please.
Sir, can you please explain again why we are taking XOR EX?
XOR EX, I mean, basically we are setting EX to 0. If you XOR any value with itself, what will you get? It will get all 0.
Yes.
Right? So we want to set EX to 0. So there could be multiple ways of doing that. For example, I can move the constant 0 to EX. I can subtract EAX from EAX, but XOR is a single cycle operation. So that's I mean, these are certain, I should say, idiosyncrasies of assembly programming, which is used in optimization, which you have to understand. I mean, XOR has no meaning here. So all that you want is you want to clear out EAX, because in EAX you have got the return value, right? So you want to clear that out, because later on you are calling a runtime check function, which will also return its status in, I'm sorry, after that you are doing a compare of two values, right?
Yes.
Immediately after that you are comparing ESP and EBP, right?
Yes.
Now that compare will set this as well. So you want to clear out EX. That's what all that you are doing.
Thank you.
Any other
So
question?
why is a push faster than subtracting the base pointer? Or subtracting from the base pointer?
Why?
I think is like push not equivalent to doing that same thing, or
No. Subtract will have to do a lot of things. It is an ALU operation.
and so what does push do? Doesn't push do like effectively the same thing? It
No.
effectively subtracts a value.
No. That is in hardware. That is not on value. That is on the control circuit. Do not confuse between a subtraction happening in terms of your subtract algorithm and subtraction happening in the control logic. Push's subtraction is in control logic, right?
Okay.
It's in the micro instruction of push. Have you studied micro instruction?
No, sir.
Like each one of this assembly instruction is realized through some very micro level operations which are equivalent to what happens in the hardware. So like every assembly instruction can be viewed as a function in terms of micro operations, and those are called micro instructions. So basically micro instructions are what hardware realizes. Hardware directly does not realize a push. So these things are done at the micro instruction, so it is directly happening on the hardware. That is much faster than When you do a subtract, you have to do a general, subtract routine. All this carry, etc., all that you'll have to be done. Because it's a general subtract. It does not know that you're subtracting the subtracting 4 or subtracting 8 or something like that. Right? So it's
But then
multiple.
people have found out that doing 3 pushes is slower than doing one
Yes,
subtract.
yes. So this is all heuristic optimization knowledge that goes into the translation and optimization process. So that is a whole lot of optimize. I mean, for example, if we optimize it even further, the whole of the add operation will disappear.
Okay.
Because of the simple reason I'm calling add with 2 and 3, which are constants.
Yeah, so it can be
So the
elided.
compiler will fold that constant and will call add not with AB being defined as 2 and 3, but will call add with 2, 3. The moment it gets a call for add with 2, 3, it can fold that, can evaluate it at the compile time itself. So it will make it 5, and it will be able to set that to C. So the whole call function will disappear. The variables AB will disappear because they would not have any role any further. Only C will exist, right? So it depends on what level you optimize. So my main focus is not on optimization. My focus is on the activation record. But naturally, the moment you touch the assembly language, there will be certain assembly level optimization idiosyncrasies which you'll have to deal with. So you'll have to understand them semantically, not syntactically. Syntactically, it looks an XOR. Syntactically, this looks a push. But semantically, it is meant for something else. Once you read assembly for a couple of times, you will start understanding. Initially, it looks great. Naturally, the first time I read, I was scratching my head at what's happening, why push ECX. But then you realize the side effect that what they're looking for. Okay. So, Chalo, let me just do a quick bit more and close. I have less than 10 minutes. Okay, so forget this. So I'm on 6.26. So this roughly now what I have done is I have basically from the numbers, I have drawn it on a schematic basis. That in main, what did I see? I see C, D, C, B, A at -12, -8, -4, so I put it. This is at 8 and 12. What are these 8 bytes missing? One is which is the EBP, and the other is the return address, because you'll have to keep the return address. Right? So if you calculate on that, you will see that these 2 places, this is actually the EBP, and this is the place for the return address. Similarly, if you look at the activation record of add, which will then have the value 996. So at 996, what will you have? You will have the EBP of the parent. So that's a control link. So it's a EBP of the parent. So 996 will have a value which is 1024, because 1024 is the address of the activation record of main, which is a value of EBP, and 1000 will have the return address if add will call some. And then on this side, -4 will be Z. On this side, X and Y, the 2 parameters. So this is a very simplified layout of a activation record. Right. So I've tried to schematically show this. And mind you, one point you'll have to keep in mind that this is nothing. I mean, this is just a design choice. So you just take a different compiler, or you just take a even different optimization option on the same compiler, you might see a little bit of different layout. Right? So it is always important to semantically understand it, not syntactically be very fussy about which value is going where, but semantically understand that these are the values that has to go in. So it shows the schematic here that the saved base pointer, this is the 1024 or 996 is here, which is where your base pointer is pointing to. So saved base pointer is a pointer to the parent. So this basically gives you a link to go to the caller, go to the caller, go to the caller. If you are kind of say, if you recall, say stack unwinding, you will get one rationale of why you need this. Right. So this is a quick way to go to the parent, go out. So this is one. Below that is the return address, 1028 or 1000 is the return address. And then on this side is the parameters. And on the other side are the local variables. Right. So the return address and parameters are on this side with the reason that this is adjacent to the activation record of the parent. So parent can easily compute from its activation record and write this, and parent knows the parameters because it knows the declaration of the function. Mind you, the parent does not know the local variables because parent does not know the definition of the function. So it cannot touch this side, but it can always go ahead and put things on this side. It has not shown the place for return value. If you will return through the activation record, then there will be a place for the return values. On the other side of the base pointer, you have the local variables, as you have here, this minuses. And then on top of that, you have saved the registers that you want to save. Right? So this is the basic schematic of this registers you already know. And I will leave you with this slide 28 and slide 29 and slide 28 and slide 29, in which actually instruction by instruction I have given a trace of what's going on in the different registers and in the memory. So based on the activation record layout that we have discovered from the assembly code. So if you go through them step by step once, I think you will have it in very clear in your mind as to what is happening at the runtime. Okay. So I think today I will close here because we'll have a small break and then Professor Mitra will talk about the second assignment. In the next class, I will talk a little bit more about optimizations and IOs and a little bit of other data types and closer runtime discussion. If there is any quick question, I can take that. Anything? No. Okay, good. So, Professor Mitra, we have 5 minutes break and then we will start.
Yes, that's better. Okay. So we will join at 3.
Please join at 3.
After 5 minutes.
After 5 minutes.
So
Thank you very
much. That's a different topic. So they need some time. Okay.
And Professor Mitra, I will sign out. I have to go to studio.
Okay, no problem. Sure. do you able to see the presentation?
Yes, sir.
Okay, thank you. So before I start for today's laboratory class, the presentation and the assignment, so a couple of announcements. So we already circulated the group that you formed. There was initially some confusion and mistake by some of the groups. So we mentioned that today is the last day. So please check carefully and reply to our TS rejoining if there is any mistake you pointed out or you wish to change your partner for any reason. After today, we will finalize this group and we will upload in the Moodle. So it will be there. So for our purpose and for your purpose also. But for you, it is not more required, but for grading purpose, we will be using that one. But this group will be used from assignment 3 onwards. Assignment 2, which is going to be released today with a 1 week of deadline, that is also individual assignment like the previous one. So please make a note of that one. That is first an announcement. Second announcement is that we already circulated one email and some of you have requested for the email for the access to departmental systems. So here we created few desktop systems and the VPN is also created. Still, if you feel that there is any problem in your system for this Linux or say support of the architecture, do not hesitate to drop an email for an account. And that in that account, first you have to log in using VPN. And after logging in through VPN, then you have to log into the system using your roll number as login and password as the password. The password is individually created, but you are free to change your own password. The same system will be used by multiple people, but in Linux, it will be protected by your login and password. So there should not be any excuse that somebody has copied my code, etc., because password that we created is also different. So keep that in your mind. And third one is that I heard that some of you has come back to the campus and also being in charge of the software laboratory. One request came to me that what will be the schedule for the laboratory that I mentioned to the respective faculty advisor. If you do not get that information, in the annex building, the first floor laboratory will be opened from 9 a.m. to 5 p.m. during working hours, except weekends and holidays. You are supposed to sit there, but you log into the system. Actually, 4 systems we identified and we upgraded with the Plex and Bison, which will be used for further assignments. That's why we are insisting that you get a login in that system. Regarding that, you can talk to the software lab. If you have any problem for anything, so you can drop me an email. Okay. So these are the announcement. Now let us start today's discussion. So today we will be discussing in the context of our second assignment. What we are planning to do in the second assignment is that instead of using the library function used by C or C++ for writing or printing, I mean for input and output, we will be implementing the same using assembly language program, and we will make them as library function so that in future when we will say target our code for one particular architecture, then instead of using the library function for printing and scanning, we can use our own library function which will be implemented in assembly language. So that way you can get rid of the dependency of printf and scanf statement in general. That we are going to discuss today. First thing, and second thing is that once you will have your own library, then how to create an archive or how to make a shared library, so that in future, instead of say has include then stdio.h kind of thing, you can during compilation process include your library like what we used to do -lm in case of including the math library. When we include the math library, then during the compilation process we provide -lm, and that includes the math library. So how we can do that one, that also we will discuss. Finally, one thing we will discuss, that how to write a make file. Okay, so the make file, I'm not sure how many of you have already used the make file, but this make file is an utility program. So if you write that make file, you will see a lot of advantages are there for this make file. And if you have ever installed any program using the source code in Linux or Unix systems, then definitely you are familiar with this make file. Usually during the compilation process from the source in the Linux, the first command you need to hit after configure, of course, the configure will read your system information and then dynamically generate the make file itself. Then you write make, and the moment you write make, then from the source program it compiles and it generates all the executable file. Then you write make install and it will be installed. Okay, so in this context, if I say mention this one, then it will not be a very bad idea that in Linux based installation for from the source code, usually you write .configure or insert .config. You need to write this one. So configure is an utility program which is also supplied to you through in the source program. What it will do, it will fire a number of systems call like uname that you read. So uname will give you that what is your architecture, what is your operating system, that information. So based upon that config, it prepares one make file. And after that configure or config, you need to type make from the terminal. Everything this I am explaining, you need to do from the terminal. So $. So either this or this, not both. In some cases it's config, in some cases it is configure. Then if you do make, then it will keep on compiling all the source programs. After compilation is done, then you go for make install. Make install, and if you type make install, then all the programs which are compiled will be installed, and that way you can install any software in your system. Okay, so let us start today's discussion. Here is a simple C++ program which uses the library function IOStream. Okay, and has include IOStream using namespace std int main cout my second program. I am printing only this, then return 0. If some of you are not aware about the C++ program, then this is same as the C hello world program. In case of C, instead of IOStream, you include stdio.h. stdio.h, and you are printing say my second program. Now this cout, or in case of C, the printf statement, for both of them we need some library function like IOStream, where as of now you know that the function definition is given. Now if I do not use anything like cout or printf, it is just assignment of some variables and calculating some arithmetic expressions, etc., even using some for loop, then I do not need to include anything like iostream.h in C++ or stdio.h in C++. So this inclusion of this header file is required because I am using some library function which is defined in this iostream or in stdio.h. Okay. Now, if this is your program, if I call that as a second 0.c++, you can compile that, you execute, you will get my second program. You have done assignment. Now from this program, if I wish to generate the assembly code, then you know that using -s or S option, I can generate the assembly code. Okay, I will go to that one. Before that, I am showing you another variation of the C++ program which performs the same thing. So in the last case, you see that I included has include iostream, and inside the only function main, I wrote cout my second program. If you are not familiar with C++, then instead of cout, you can write printf within double quote my second program. Of course, parenthesis will be there. And instead of iostream, you write stdio.h. Using namespace std is not required. Now, instead of cout, I can use existing system call like write. And if I use write, then the corresponding header file for write is not iostream, rather unistd.h. Since I am using write, whose definition is given in unistd.h, so I am including unistd.h and I am calling function write. Now inside the function write, as an argument, I need to pass 3 parameters. The first parameter will indicate writing to where. Where do I write? Now, probably you know in Linux, everything is considered as a file. Standard output, I mean the terminal is also a file. Keyboard is also a file, along with the file in usual context that you studied in PDS is also a file. Now the first parameter will take the input where to write. Now regarding this where, I wish to write on the terminal because my cout was writing on the terminal, printf will write on the terminal, and here also I am writing the same program in a different way without using cout or printf, using the system call. And this one is an integer constant. It is an aliasing or defined state macro for std underscore file name, std out underscore file name. So one here indicates that it will write to the standard output. Okay, followed by what I need to write. So the first argument is where to write. The second argument is where to write, which one to write. Which one to write? Here I am telling one string I need to write. Then I need to say that what is the length of that string. So these 3 arguments it will take. Okay. For that I did what? I defined length as 19, has defined length 19, and I declared one variable str string of length 19, which actually consists of my second program /n, that is new line. Now the number of characters, if you compute 1, 2, space is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, up to /n, it's 18. But you know, since it's string, inside a double quote. So after this one, there is one more character, which is the null character /0. Considering that 18 plus 1, so is my 19 here. That is my length. Also, you noted one thing from this write system call, that it is required that where to write information, which one to write information, and what is the length of the write information. But it cannot differentiate between, say, integer or floating point number or, say, character. Between that, it doesn't discriminate. And also, if you think carefully, then you will understand that meaning of integer, floating point, or character is different when I am performing some computation. But when, say, I am printing, then I need not have to differentiate 1 to 3 means, I need not have to differentiate whether 1 to 3 means integer constant or 1 to 3 is character. I do not wish to discriminate between those two, right? So that way, this write is making a generic or general assumption that whatever I will print is nothing but the sequence of characters. Very good. If it is sequence of character, then the same problem that we discussed in your PDS class, how do I know that whether it is the end of the string or end of the character sequence or not? Two ways I can do that one. Either I will read the /0, the last, or I will look for the length. So here it is taking the length. So the length will be taken as the third argument. Finally, it is exiting, and this write and exit is within this header file unistd.h. So we get rid of cin, cout or printf, but now we are with system call write. Let us see what more we can do with this one. Now this program, if we compile using, say, -s option in order to generate its assembly code, then what we will see that these are familiar with you. So the name of the program .file, then text, global main, type main, function main, then I'm starting from here, CFI, start proc, etc. So you are familiar with this, and I am not going into detail of that. Now, the point we wish to discuss is that after creating a space in order to store the string, which string? This my second program. Okay, in order to store that string, so what it does, it creates the space. So RAX is assigned to MRBP -8. Then just now in the class of PPD mentioned that XR is used to initialize this with 0. So it is clearing of any register. So XOR, if you look at their truth table, then you will see that if both the bits are same, then it will be 0. Otherwise, it will be 1. Now, if with the same content, I will perform XOR, and the fourth character L indicates that long, right? That we studied. So then EAX, EAX, it will clear the register and it will assign as 0. Next, I am moving again long, fourth character is L. Immediate number is 1931508045 to one base pointer location RBP -32. Now, what does this decimal number indicates? If I convert this decimal number to its equivalent binary, then this is my binary number. If I convert this binary to hexadecimal number, this is my hexadecimal number. And if I consult my ASCII table, then I will see 4D corresponds to capital M, 79 corresponds to small y, 20 corresponds to space, 73 corresponds to small s. Next, 1852793701. If I translate, then I will get 6E, 6F, 6365. That if I convert using the help of ASCII table, then ECON. And that way you will see that in reverse, my second program, that string is being stored. So MY space S ECON D space PROGRAM/N. So in reverse, it is being stored, my second program. Okay. After this /n, I know that there is a requirement of storing /0. So /0 is also being stored. And since /0 indicates 00, null character in hexadecimal 00, which means in binary it will be all zeros. And that is why in decimal 0 is moving to RBP minus 14 location. After that, so I am loading this information REX to RBP minus 32, that is my string location, and the length of the string, that is 19, I am also loading that one in EDX. Next, RSI, here it will be actually RSI, so this will be RSI. RSI is loading RAX. What was in RAX? The location for the string. And in EDI, I am storing 1. 1 is the integer. Then I am calling the function call write. When I call the function write, then it will expect that its first argument will be in EDI. And first argument means what? First argument was where to write this one, that is my standard output. Then the second argument will be in RSI, that is the location of the string from where it is starting. Okay, RBP minus 32. So this RBP minus 32, that is the starting position of my string. Then the length of the string, the third argument, is stored in EDX. So write will assume that in EDI my first argument, in RSI my second argument, and in EDX my third argument is there. With that assumption, when it will call write, then basically it will write my second program /n on the terminal, right? So we have done that programming using the system call, and we get rid of printf or cout. Now let us see what further modification we can do. Here we are including another header file syscall and unistd. So last time I just included, here I am telling that in your system, if you are unable to locate unistd using locate function, LOCATE, okay, then you can look for ASM, the assembler folder. Then in the macro, I provided stdout_filename1. Next, this is my assembly code. So this header information I added, but rest of the information is same as like the assembly code. Okay. Here, what I am doing, instead of writing, you go back, here you see that function call was there, and that was write, call write. Now I will call one software interrupt, it is syscall. Syscall is a software interrupt that when it will be called, so the current processing of the program will be paused and it will provide a software interrupt to the operating system to perform some function. So what function? That function will be determined by looking at the content of RDX, RSI, RDI and EAX. So the content in RDX, RSI, RDI and EAX will tell the operating system what operation it needs to perform. So now you see that when I am using printf or cout, then corresponding to that one, I have one code in the header file. I am invoking that one. And it's the system or kind of system call is completely, say, black box to me. I am just relying on printf and cout. But right now, when I am unfolding that or opening that black box, then I see, okay, what I need to do, I need to call the syscall. When I will call syscall, then it will, syscall is just a software interrupt. It will call, it will process the request in operating system. So it will actually process one service requested by operating system. And which service it will process? That is determined by the content of these four registers: RDX, RSI, RDI, EAX. So first EAX, the content of the EAX, if it is 1, it says that you need to perform one write operation. So instead of say $1, you can write within parentheses sys_write, because the assembler will understand that this is aliasing of 1. But you are free, you can directly write 1 here also. Next, if the content of RDI, another register, is 1, then it understands that, okay, I have to write to the terminal. Again, you can write $1, or you can use this aliasing. Specifically, if you use this aliasing like syswrite, stdout_file number, then you can in future also able to understand that, okay, what I am trying to do. If you write say 1 only, then you have to again consult if you forget that 1 means which device or 1 means which operation. But if you write this way, this syswrite stdout_file number, then it will be easy for you to figure out that what actually I am doing. Okay, so the content EAX indicates that the software interrupt is given for a write operation by the operating system. Then the write operation will take place on the standard output device, that is my terminal. Next, you write the string which starts from the location. This L1 is coming from the level here. This is my L1. And what is the length? If this is my L1 and this is my L2, then the difference L2 minus L1 is the length of the string that you can write here like this and load it in RDX, or you can somehow like this stdout_file name, like that way you can define that one. But if you define that one, then your problem will be that you may currently you are writing my second program, but in future you can write something else. Then how do you dynamically decide what is the length of my string? So that is not possible. So that's why it is a good idea that if you use this L2 minus L1, which will actually store the length of the string, then you call syscall and syscall will print. So this part will actually print my second program on the terminal. And you see, when you are directly using this one, then you did not have to worry about other header files. Once it is done, then you have to return that return or exit statement, and for that return sys exit. So 60 is the number for the exit. It will be loaded to EAX. Now you see why I said that you can definitely do $1 and EAX for write operation. Here you can do $60, % EAX for exit, but then you have to remember what 1 means what, 60 means what. Instead, if you write sys underscore exit, then to some extent you are knowing that, okay, I am going for a system call of write. Here I am going for a system call of exit. But this is kind of a macro whose definition is given here in syscall.h. Then you are moving 0 to RDI because I wish to return with the value 0. That is what was there in this program. Exit 0. Okay, so this 0. That I am considering here. So 0. Then I am again giving the syscall, then software interrupt. What it will do? It will just return. Okay. Now, okay, before this one, up to this, do you have any question? Do you have any question? Okay. Then we can continue. So you wrote this one using x86-64 software interrupt, that is syscall. You wrote this program and it will write on the terminal. How do you compile that one? So that was an assembly language program, this .s. Okay, and everything is written in assembly language program. You can use the program CPP, libcpp for the pre-processing. Now you see that capital S will be converted to small s. The difference is that here I have two header files that I need to pre-process, because pre-processing is the stage where the header files will be inflated and the comments will be removed. If there is a macro, those will be taken care. And finally, one assembly language program will be generated, complete program. Okay. Now this AS is the assembler. Last time during assignment 1, we used GCC or CC compiler for generating the assembly language code, and even from the assembly language code to say object code, we have used that CC or GCC. But AS is the assembler which will take the assembly language program second3.s as input and will generate one object file .o as output. That is the output of the assembler. If there is no library dependency, then this you can also consider as the executable file. So this executable file will be loaded by the loader and you will get the final output file, that is a.out, as an executable file. Now if you run ./a.out, you will get the print minus second program, my second program. Okay, so to summarize what I did, using the software interrupt, I wrote one small assembly code where I called the syscall, the software interrupt, in order to write or print on the terminal one string. That string I defined. That string I wrote here, my second program. Okay, and then using the preprocessor, I expanded that one. Using the assembler, I generated the .o file, object file, and using the loader, I loaded it in order to generate the executable file, and when executable file is executed, it is printing my second program. Okay. Now the same thing I have, so this here I have done my second program, but as I mentioned that when I am say printing on the standard output, hardly I will differentiate between say array of characters, integer constant or floating point, because everything will be just printed. So those discrimination is required for the calculation purpose, right? So that's why if instead of array of characters, I wish to print integer, following the same procedure, I can do that one. Only thing I need to do is that I have to store that integer. You know that when it is integer, so any integer constant, say you can store in 2 bytes or 4 bytes, right? 4 bytes means 32 bit. Now the integer, if I convert to a string and use the previous program, then I can print the integer also to the terminal or the display, right? For that, I am actually defining one buffer size of 20. It is up to you. You can increase this one also. This small program void print underscore int is taking integer n as an input and converting it to an array of characters. So if it is say 1, 2, 3, 4 integer value, then it is converting to 1 within single quote, 2 within single quote, 3 within single quote, 4 and /0 at the end. Now if you follow this program, so character buffer, I am declaring one array of characters. I am initializing 0 as within single quote 0. Integer I0 j k bytes. If n equals to 0, which means the input is 0, then buff I plus plus equals to 0. 0 means what? Character 0 I am storing as buff 0 position. This is post increment of I. So after storing this character 0 in buff 0, then I is now 1 incremented. If it is not 0, then there are two possibilities. My integer can be negative or my integer can be positive. If it is negative, I am testing that. If it is less than 0, then I am storing hyphen or say negative sign as a character within single quote as the first character. So buff 0 and then further incrementing. Next, what I am doing, since it's a negative number, I am taking further negation. So negation and negation will be positive. So n will be positive now. Okay. Next, in a while loop, it's very simple. You can see that one. I am taking the modulus. I am storing it in buff. And while I'm storing it, the digits are being added with characters 0 and is typecasted with character, so that it will store as a character instead of an integer. So up to this digit it is integer, but when I added that one with 0 character and typecast with the character, then actually it is converted to one character. Then this is the division. I'll keep on iterating, and in the process, if say my number is -1234/0, so what is being stored? So it is stored at the first position 0, and after that one I am dividing by 10. So from the backward, so 4, 3, 2, 1 it will come, right? Next, if buff 0 equals to minus j equals to 1, else j equals to 0, ki minus 1, here I am actually changing the direction. So I stored 4, 3, 2, 1. Now I am making it just reverse 1, 2, 3, 4 in this while loop. Then finally I am putting buff I, the last character, as /1/n, so that after printing the integer, the cursor will not stay right after the integer, rather it will come down to a new line. That's why I'm giving /n. So number of bytes or the number of characters I stored, or the length of my string, which is nothing but the integer, is I plus 1. Now this is the piece of assembly code. Now as of now, what you have seen is nothing but a C program or C++, whatever you may think, right? But this printf, instead of printing that one, I am calling the assembly code for printing purpose. So inside the C program, if you write anything, double underscore ASM double underscore, next double underscore volatile double underscore, and within parentheses, if you write anything, then this is going to be part of the assembly language program. C will understand this is from assembly language program. Otherwise, for this statement is kind of alien to C program. So C will not understand what is this. This is not as per my syntax. But if it is inside this one, then C will understand, okay, this is actually assembly language code. So I have nothing to do with this one. I will take care of about the rest. But when the assembler will come in order to convert it to the machine language, then he will take care this part as well as this portion, which is converted by me to say assembly language code, right? Now what you see here, that move L $1, you remember for the write it was $1, for the standard output file number it was also $1, and I mentioned you can write $1 instead of using say syswrite or stdout underscore file number. This double percentage actually to discriminate the register from the argument. So it is used only in this kind of situation. As of now, we have seen only 1% is required for the register, say EAX. Now for this, so it is a small piece of code, but for other code or assembly code, if somebody is interested to write, then in order to mention that it is an argument, then %EAX is used. And if I give double %, then it says, okay, no, it's not actually argument. This is the register. So in EAX, I mentioned that, okay, you enter the write operation, and this is the write in the standard output. Then syscall and sbuff as an argument. I am passing that the location for the buff, and this is my length. So you remember the start of the string and the number of bytes, both are being passed. So syscall, what it will do, that syscall will actually print that particular integer onto the terminal. So here is one comment that $4 is write, $1 is on stdin. Okay, so this okay, so I think I make a mistake. So it will be $1 for write and $4 is for stdin. Okay. Now that was one function for the printf. How can I use that one? This is my actually the main program. In this main program, I am making an entry for my function void print underscore int. This is my function. Okay. So if not define my print int underscore h, then define my print int underscore h void print int end of f. I believe that you are familiar with this kind of conditional statement, that if my print int underscore h is not defined, then only it will define, otherwise it will not define. Otherwise, if I go for multiple definition, then the variables which will be used or even the name of the function, there will be a conflict, which one to include. So I see that two definitions are there. Now my print int.h is the name of this particular file. Okay, so the printing an integer, this function I am storing as my printing.h. This is one printing, this is the main program. has include IOStream using namespace std include printin.h. That was the program I just mentioned in previous slides. So this IOStream I am including because I am using cout and cin both as of now. But you see, I have one printint n, and where it is defined? It is defined here. And in that printint, if I go back, you will see that nothing is included here. So there is no dependency on the existing library function. That means if say I remove this cout, cin line, I do not need this IOStream and neither this using namespace std, then I need to initialize say n equals to say I write say 150. Then this program is good enough to print 150 on the terminal. And where is there? In printin.h, a small piece of assembly code and another C code which converts 150 to a stream of or sequence of characters. Okay. So up to this, do you have any question? Okay. Now, how can I create the library? Now it's very simple. So you have seen that this is my main printin.c program. So I am compiling that one. But you please note it down that I have one dependency has include printin.h. That's why I cannot directly compile it in order to generate the executable file a.out. This printin.h is not yet compiled or included, right? So that's why what I will do that I will just compile it so that I will get printint.o object file. So this is the C++ command, and this regarding this WALL, it is optional. I use this one. AR is an Unix command for archive. So I am archiving this object file printint.o as libprintint.a so that in future I can use that archive function. Next, if I compile that my main printin.c C++, so I need to compile both. I need to compile this one and I need to compile this one. So separately I am compiling both. So one is main printin.c, another printin.c. Compiling both, generating .o file. But for the printint function, which is converting the integer to array of characters and then calling the system function syscall in order to print, for that I am archiving the object file with name libprinting.a. Next, what will happen? In this line you see that now I am linking C++ main printing.o, that is the outcome of just the previous line, the object file of main printing.o minus l dot minus include printint. So this printint is nothing but this one after archiving. If you say do not do this archiving process, then separately you have to write C++ main printin.o printin.o again. Then also you will able to do this one. But here we are demonstrating that how to create your own library. So after creating the object file of printin.c++, then that object file is archived using AR. And how to use that archive? So minus L printint, that's it. And you will get the executable file by default a.out. and if it will say enter an integer, which was written here previous slide, so this I removed. Let me erase all. So this line, enter an integer, so it will be printed here. Then I am entering -1, 2, 3. It will input using cin, so n will store -1, 2, 3. Next, the -1, 2, 3 is being printed using my own library function, print_int, right? So that way I can create my library function. Up to this, do you have any question? Okay. Now, after creating the library function, so here I mentioned that this was the last slide I discussed. Here I mentioned that the C++ main printing.o, and then you need to include -l printint, you have to mention. But how about if I store this printint into some standard library folder so that automatically it will be called? For that, what I need to do is that cp libprintint.a, cp is copy, /user/lib. In user lib, I am copying that one. And when I am copying that one, then that l dot I need not have to mention. So directly I can call that one. So here you see the modified version. So that l dot is no more required here. But in order to perform this copy operation, as you see that it is /user_lib. So you need the root privilege in order to perform this one. Okay. Now, if you wish to create a shared library, then these are the steps. So you compile. Now you use the option -fpic compile printing.c. It will generate printing.o. Then you use flag shared -wi -so name libprinting.so. So .so is my shared object library. -o libprinting.so and printing.o. So this printing.o, which I got from here, will create some link and the file name libprinting.so. That is my shared object file. Next, if I copy that shared object file to user lib, definitely you need the super user access, and then I go for ld config. So I change their configuration, that user lib, so that it will also include the information regarding this printing.o. Then we are done. Additionally, you can create one soft link libprinting.so.1 under /user lib, and if you create that one, then it's not you, anybody in that particular system can able to compile a program like this, and anybody can use the library function that you have developed. The new ./a.out does not contain the code of printing, but it contains code for the corresponding PLT or procedure linkage table. So that is one of the reason that when usually you compile your program in say one system, the same program is not running in that same executable file, actually is not running in another system. Because in this program, when this library has been used, definitely some library will be used. Then those libraries are shared and they are dynamically linked. in the executable file like a.out, that complete code of the printent is not being copied. It is not being copied. Only a PLT has been copied. So during program execution, it will look for that PLT, it will fetch the corresponding code and it will execute. And you understand, it is advantageous, right? Say in a system, if say in a desktop also, if say 131 students are logged in and using printf statement. Now corresponding to each person's printf, if the complete code of the printf is actually contained inside or is pushed inside your C program and hence the a.out, then individual's executable file size will be very high, but that is not required. When the program will be in execution, when you will see, okay, this is printf, I know where the printf is. If only that linking, that procedural linkage table information is provided, then during the runtime, I can pick that one. Now you understand, if during the runtime I can pick that one, then if I change my system from one system to another system and just copy not the source program, it will not happen with the source code, and just copy my executable file, then in the different system, when it will look for that particular library function, in our case the printint, it may not able to find in the PLT provided previously. If it is the case, that executable file will not run. So this situation you may encounter when say you are say installing some software and you downloaded some executable file. In some system it is being installed, in some system it is not being installed. Most of the time you will see the error it is showing is some .so or .so.1 file is missing, or it is not able to locate or say link, that will be mentioned there, which means nothing but the executable file has a dependency on that particular library function. Unless that library function is properly configured in the proper location, it will not able to perform its desired function. So two ways to deal with the situation: either you get that library function and put it in the right place, then your program will be in execution. Otherwise, you get the source code instead of the executable file, you compile in your system, and you will see when it will compile in your system, then the corresponding library it will pick and it will create its own PLT, procedural linkage table. Then also it will run. Okay. So those are some of the system level issue. If you have laptop and time to time if you wish to install something, then you can able to see that one. Up to this, do you have any question? Okay. Then we are going to the final topic for today, that is the makefile. Makefile is an utility program that automatically decides which part of a large software is required to be recompiled. That is one of the most important information regarding the makefile. As a component, there are three components in the makefile: target, colon, prerequisites, next line, command. Target indicates name of a file generated by a program, main.o or certain action like clean. Prerequisite, files required to create that target, main.c++, xyz.h, etc. And command, using which command you will use these prerequisite files in order to generate this target file. Okay. In some previous version of the systems, this make file was not free format. Was not free format means that this red color indicates target, this black color indicates prerequisite, and this pink color indicates the command. So there was a particular format like this command. So after this target and colon, one tab will be given, and there will be two tabs at the beginning of the line for the command. So those kind of restrictions was there, but nowadays in the recent systems, most of the time it is not required. Nevertheless, keep this in your mind. If you find that after writing a make file, it is not executing, then you please check that whether there is any formatting options or not. This is actually the content of one make file. So it says a.out, my final goal, colon, will be created from main printing.o libprinting.a. From these two files, a.out will be created. How will it be created? Using the command C++ main printing.o object file minus dot L capital L dot minus this include I print int, using this one. Now how this main printing.o, which is required for a.out, will be created? When main printing.o is the target, it requires the source code main printing.c++ and header file printing.h, and its command is C++ minus C compilation main printing.c++. How this lib printing.a will be created? From printing.o, that we have seen that archived command ar minus rcs libprint int.a printing.o. Now how this printing.o will be created? Printing.c++, printing.h, and compiling minus with minus c option printing.c++. Okay, now you see my final target is a.out following this second line command. Now I need main printing.o and libprinting.a. How I will get main printing.o? Using main printing.c and header file using this command. How I will get this archive file? From printing.o using this command. How I will get printing.o? Using these two source files. So between these two source files there is a space, no comma. Okay, and using the command like C++ minus C printing.c++. Optionally, you can keep one option clean colon. It doesn't need any prerequisite, but the command is rm existing a.out file will be removed and all the object files will be removed along with the archive file, because you wish to clean everything and you wish to create again. But also some people would like to have a clean function where these object files will be removed. This will be removed and this will be, only these two will be removed. Okay, so these two will be removed, because once I will get a.out, then I do not need any object file. So in order to save some space, I can remove that one. That is also kind of clean. Usually there is a convention that if you give your make file name as make file like this, M will be capital, no space between make and file. If you give this as name, then keeping this in the current folder, if you just type make, small make, M-A-K-E, if you type that one, then by default it will call this file. But if you give some other name, then after this make, you have to provide the name of that make file and it will call that make file. Now if you just type make, then what will happen? Make clean, as I mentioned, everything will be removed. But if I type make, then what will happen? You see, first a.out it is trying to create, but it will not able to create that one, since these two prerequisite is not met because these two are not created yet. So it will try to create main printing.o. So corresponding to that, the command will be fired first. So this is my first command. Next, it will get this one. Now it will try to get libprinting.a. It is not with me. The target libprinting.a says that I need printing.o. It is also not with me. Then target printing.o says that you fire this command line and you generate printing.o. So my second command is to generate printing.o. Once you will generate printing.o, it will go back here and following this AR archive function, it will create libprinting.a. So archive function following it will create this one. Now I have this one and this one. So it will go back here and using this first command, it will create the a.out file. A.out will be generated. So you just type make and everything will be created one after another. Finally, you will get a.out. Now, the advantage of makefile, I was explaining that it is just considering two source files, but there may be say several source files, specifically when you are developing say one package. Say for example, you are writing say one compiler, or say you are writing one small operating system, or say one programming environment. Then you understand the number of source codes or the number of files, source code files will be very high in nature or very large. Now you build the executable file, suddenly you locate, okay, so in one program there may be some mistake. Then you change there in that program, and if you type the make, then it will not perform all the steps. Rather, it will look for the timestamp. If the target file's timestamp is after the source code timestamp or prerequisite file's timestamp, then it will not fire that particular command. And that way, you can save a huge amount of time for the compilation process. Say for example, that if there are 100 source codes and you are writing a makefile, so it will keep on compiling 100 source codes, then it will creating the library, it will do the binding and finally generating the output file. And let us assume it will take say about 5 minutes or so, depends. If it is not say 100, more than that, it may possible. Now, if you change only one source code, and if you do a if you wish to perform the same steps again, then again 5 more minutes it will take. But if you write in makefile, then it will check that only the file, only the source code whose timestamp is after its object file's timestamp, it will generate only that object file, or it will compile only that source code, and all other commands where there is a dependency on this particular object file. Okay, so that is also an advantage of this makefile. So that is mostly about what is you have to do in library function. I will go to the assignment. Okay, so one final thing, that if you are really interested to know that what is inside in the object file, then you can fire this obj dump -t dissect or deassembly second 3.0, then you will see something like this. So here this is the instruction, machine level instruction corresponding to the assembly code this. This is the machine level instruction corresponding to the assembly code this. It will be discussed in detail during the target code generation process. When say from this assembly language or say intermediate representation, you will be generating this code, then you see that there is a fixed number of assembly language programs, and corresponding to each such, you will have one mapping table. So you map that to the corresponding target code. Okay. So that's all about the presentation. Now, if you have any question, please let me know.
Sir, can the make file compile circular dependent file?
Can you be a little loud?
Can the make file compile circularly dependent files?
This object file you are talking about?
Yes, sir. Like A is dependent on B and B is dependent on A. Can it compile that?
Oh, during the compilation process, you are talking about circular dependency. I
Yes,
cannot
sir. Yes.
recall. Yes, so I cannot recall it any such action. But if there is any, then definitely you can understand that it will be it will compile. So during the make file, it will compile all. There may be possibility. But during the program writing, generally you will not write that way. Usually what people used to do, either corresponding to a function, you write one file, or corresponding to one activity, you write one file. Okay, any other question? Okay, then let me share with you the second assignment. Do you able to see the second assignment? The PDF file?
Yes, sir.
Okay, very good. Thank you. So in the second assignment, so assign date is today, and the submit date is 1 week from now. So actually the next Wednesday midnight. Now marks is 50, but you know that these marks actually will be weighted. So usually that weight will decide later. So that will be weighted. So we expect that it will take all the assignments seriously. Now here we mentioned write a C, but here you can also consider C++, C or C++ program consisting of the following functions to create a library. You cannot use any standard library function. Okay, so we demonstrated one for print underscore int. So it prints the third one. So it prints the signed integer with left alignment. Printing sign for a negative number is mandatory, while for a positive number, it is not required. On success, function will return the number of characters printed, and on failure, it will return ERR. What is ERR? I'll come to that one. Okay. Next, printing a string. So one similar problem we also discussed. So it will take the array of characters. In print int, it is taking int n. Then you remember that we are converting that one to array of characters, and then calling the assembly code syscall in order to print that one. In case of print string, that conversion is not required. Directly we can call the syscall in order to print the string. It will be terminated by /0. The return value is the number of characters printed. Int read int integer star n. So reads a signed number in %d format. Caller gets the value through the pointer parameter. The return value is OK for success or error on failure. Now for this read int, although we didn't discuss, but as you understand that only the device you need to change from std out file number, it will be std in file number, and the system call function, instead of write, it will be read function. Corresponding to that, you need to make the changes. Now read float is same, but only you will allow reading the floating point numbers. Again, for this integer and floating point number reading, whenever you will read, you remember that you will read as a character, and after reading that character from the input device, you need to basically convert that one to the respective integer or floating point number. Now you see that for reading and printing, reading integer and floating point for both the numbers, it is star f, so called by the address. And you remember that scanf percent you provide. So what you need to do after converting to that floating point number, then you need to supply the base address of that string in this percent f. Then print float, it will be similar to the readint. Only thing is that you need to consider that all the possibilities of the floating point numbers, like it can be, there can be decimal point, there can be e means that exponential, and after that exponential there can be there will be integer constant with sign or without sign. So plus may or may not be there, optional, but negative must be there. So in order to understand this more clearly, you may consult our theoretical lecture class where we drawn one finite state machine for integer and floating point number. Okay. Now use only the following header file of your C program. Header file for assignment 2, name it as myl.h. So it contains the define error equals to 0, define OK1. So that will be considered as the return statement. Here the error or OK, so those things as mentioned. So you name your library functions like this, which is given, and that is my header file. Okay. So name your .c file. If you write in C++, you write say CPP or C++ as ASS or 2_roll.c, where roll is your roll number. Include only myl.h. No other include statement will be there as your header file. It should not contain the function main. Write your main function in a separate file. So for that, we also demonstrated in the makefile sections how to do that one. Use makefile to test your library. Move your main.c, myl.h, makefile and ass2_roll.c in folder asgn2_roll. Zip the folder and upload as a single file in the Moodle server. So please note it down that for makefile there is no separated numbering, because there are 5 functions. For each 10 marks are there, 10 marks are there, in total 50. But for missing makefile, it will carry a penalty of 10 marks. So you should not forget to upload your makefile. Okay. Now again, as a component, what will be there? One main file which will call the these 5 functions in order to show or demonstrate their functionality. One myl.h file, which you can copy this one and write that one, and only that header file will be included, no other file. One makefile to compile all your files. I suggest corresponding to each function you write one particular function and one particular file, and that as2_roll.c will be your assignment file. So if you write only one file containing all the 5 functions, that is also fine. Then you name it as ass2_roll.c. Okay. So any confusion here?
Excuse me,
Then yes.
Sir, would the deadline is Wednesday
Midnight.
midnight, right?
What time midnight?
Can it be like pushed to Thursday midnight or something? Like we'll get a full week to do it.
No. Do not take the extension right now. Lot more things are coming on the way. Okay. So why do you need one more day? I have no problem personally, but why do you need that?
Like it'll give us a full week. That's the only reason that I'm asking. No other thing.
Okay, then I will change that one. That's not a problem. Okay. Anything else? But that doesn't change our schedule. That next Thursday there will be laboratory class, and assignment 3 will be released on that day.
Yeah. Sure. And one more thing, you mentioned that we can write different C files for different functions, right? And we can do it in a single file as well.
Yes. So it's up to you. So we are not enforcing anything at this point.
Okay. So if we like make different files, so what would be the naming convention if you want to mention something?
So you can use that ASS2 then underscore printing or something, but roll number must be there. Otherwise, it will overwrite with some other guys. Or you can write in one file. Okay, so let us reduce the number of files at this moment. So in one file you write all the 5 processes. It will be a little large. So okay, fine. Anything else? Okay, I uploaded the assignment and I also approved your request that the deadline is 2nd of September midnight. Okay. So if you do not have anything else, so let us stop here for today. And our next class will be theory class, and that will be on Monday at 11 as per schedule. Okay. Thank you.